Welcome. In this video, I'll be discussing the basics of vectors, in particular what they are, what they're not, and how they can be applied to the complex number plane in the Extension 2 Mathematics course. So firstly, vectors are rays. Now, if you learnt rays back in early high school, you would have known that rays have a beginning point and an arrow at the other end. This leads us to two things that vectors must have. They must have a magnitude, which is how long this vector is, and a direction, which is which way the vector is pointing. Now the consequences of this is that, for example, these two vectors, if they have the same length, are the same vectors. Even if I put them on a number plane, like so, they are still the same vectors. They might have been translated across a little bit and have maybe interacting with different coordinates, but they are still the same vector. On the other hand, if we had a vector that had the same magnitude, like so, but a different direction, like this vector, as you can see, this vector is pointing in the opposite direction even if they have the same magnitude. Now these two vectors are not the same. So let me just divide this page up. Okay. Now the most important thing to realize for vectors when applied to the Argand diagram for the complex numbers is that they're not coordinates. If I introduce to you a vector that goes from the origin, represented by the number 0, to the point, let's say, represented by the complex number 3 plus 2i, like so. Sorry, that's the real and that's the imaginary. Then what we'll have is we'll have a vector joining the origin to that coordinate, and this vector will be called z. Now, we know what z is. Z equals to 3 plus 2i. Now, let's say over here, we've got this coordinate. Let's just make this 8, 3. I could draw the same vector z over here, like so. And this vector is still 3 plus 2i. So the way that the vector interacts with the coordinate it starts from means that the finishing point will be 11 and 5. So while these two coordinates might represent certain complex numbers on the Argand diagram, the vectors themselves represent something else. These two vectors are the same because they do the same thing to whichever point they started from, and leaves you 3 to the right and 2 up. So these two are again the same vector. Right, so the question gives you a square with point A representing 3 plus I and C representing minus 1 plus 3i. Now this is obviously the typical exam format of how they're going to word and inform you that this point on the Argand diagram represents a certain complex number. Okay, now we also know that OA, we're told that it's U, the vector, and OC is V. So I've gone ahead and labeled U and V as such, making sure I put the arrows here and the arrow there to indicate that the vector goes from O to A. Now the question is, what is the value of U and V? Now U and V are simply the complex numbers that are attached to the coordinates, to the points A and C. Okay, it's sort of like saying that U is the vector from the origin to A, and if A represents a complex number, then U is simply going to be from 0 to 3 plus I, which is simply the complex number 3 plus I. Very simple. It takes just a bit of getting used to. What is the vector AB? Now, if you're interested in this vector AB, you'll notice that because you're told it's a square, V, and over here AB, OC and AB are both parallel and equal in length. Okay, so what that means is that the vector AB is really the same vector as the vector OC, so therefore it's simply V. Now in part 3, you're asked what is the vector OB. Now if you're interested in finding OB, which is from here to there, by the parallelogram method we covered earlier, this is simply the addition of vector OA and the vector OC, so you would write it down like that. You would write OB is the addition of OA plus OC, which is equals to U plus V, which you can evaluate to be, according to these numbers, 2 plus 4i. Now if you go check on the diagram, it indeed looks like 2 plus 4i, so we know we're doing it right. What is the complex number? What complex number does B represent? Now again, you check that the point B, we know the vector here, U plus V, is 2 plus 4i. And just looking at where B is, we know that B represents the complex number 2 plus 4i. Now they also ask you what is the vector from A to C. Now this is the obviously the other type of vector addition or subtraction. In this case, vector AC is really, if you just take the negative vector OA, so it's now AO, the vector AC, according to the head to tail addition method, is going to be the vector, let's see, AO plus the vector OC, which is really just minus U plus V, or you could call it V minus U. Okay, so once you get that, you calculate what V minus U is, and that's going to be minus 4, let's see, plus 2i. Okay, the key here is to use the head to tail method from A to O, then to C. Now you might think, well, wait a minute, C doesn't look like minus 4 plus 2i. This is a problem because, C obviously represents, as we know, minus 1 plus 3i. So why does this not link to that? It's because the vector AC does not start from the origin. The vector AC starts here, and if you can understand this as a vector, you can see that if you actually visualize how the travel from A to C, you've actually have gone 4 to the left and 2 up. Now if you were to translate this so that the vector is all the way over here, then sure, this point, whatever it is, will be minus 4 plus 2i. But as you can see, when we're dealing with vectors, we are not really dealing with coordinates. We are dealing with rays. Okay, and the rays can be anywhere on the Argand diagram. Now finally, they want you to explain why this is a square. Now there are options that we can use, and this leads on nicely to the next part of the complex numbers chapter. The options you can use, obviously we want to prove that the gradient of OA is perpendicular to the gradient of OC. So you can try and prove that these two vectors are perpendicular. You might also want to prove that OA in length is equals to OC, and we have a particular language to do with the word modulus for this as well. So that will all be covered. Now, of course, we can treat all these points as coordinates and apply coordinate geometry, but later on, okay, you'll be learning how to more efficiently and relevantly explain why this is a square. Okay, so not much coordinate geometry ends up getting used here.